The engineering of the Europa Clipper is absolutely insane. This isn't just some science project for space nerds, it's a jaw-dropping $5.2 billion mission driven by sheer human curiosity and the belief that we're on the brink of an extraordinary discovery. Think about it. This spacecraft has to survive Jupiter's brutal radiation, travel billions of miles across space, and function flawlessly in one of the trickiest environments in the solar system. It's like sending a robot into the heart of chaos and expecting it to deliver perfect results. But the Clipper isn't just about collecting data, it's about cracking open the mysteries of a moon that could potentially host life. Europa, with its icy shell and hidden ocean, has long been a source of wild wonder. This mission is our ticket to finally peeking behind the curtain and exploring a world we've only dared to dream about. It's pure cosmic storytelling in the making. Exploring Jupiter's hidden ocean. In the freezing outer reaches of our solar system, a moon has captured the imagination of scientists and dreamers alike. Europa, one of Jupiter's largest moons. At first glance, Europa looks like an icy wasteland, a ball of frozen water swirling around a giant planet. But beneath that thick, frigid crust lies something extraordinary, a massive hidden ocean, kept warm by the moon's internal heat. And where there's water, there might just be life. That's where NASA's Europa Clipper comes in. This isn't just another space mission, it's an ambitious hunt for answers to one of humanity's oldest questions. Are we alone in the universe? Launched in October 2024, the Europa Clipper will travel nearly 2 billion miles to Jupiter's orbit, where it will begin its daring exploration of Europa. This spacecraft is built to get as close as possible to this mysterious moon and uncover its secrets. Here's the plan. The Europa Clipper will perform nearly 50 flybys of Europa, coming as close as 16 miles above its icy surface. That's like flying just above a skyscraper in a city-sized ocean of ice. Each flyby will focus on a different part of the moon, allowing the spacecraft to scan almost the entire surface. With high-tech tools like ice-penetrating radar and spectrometers, it'll map the ice shell, peek beneath the surface, and search for signs of the ocean that lies beneath. Why go through all this trouble? Because Europa might be one of the best places to find life beyond Earth. NASA wants to figure out three big things. How thick is Europa's ice shell, and does it connect to the ocean below? What's in that ocean? Are there the right ingredients for life? And what's happening on the surface? Is the ice shifting, cracking, or even releasing water into space through giant plumes? So what could possibly be lying beneath Europa's icy crust? Could something be swimming in that dark alien ocean? This is the insane engineering of the Europa Clipper, a mission that just might change everything we know about life in the universe. NASA's Colossal Explorer. The Europa Clipper spacecraft isn't just a scientific tool, it's an engineering marvel, the largest spacecraft NASA has ever built for planetary exploration. Standing 16 feet tall, about the height of a two-story building, it's an imposing figure. But its real showstopper is its massive solar arrays. Once deployed, these panels stretch more than 100 feet across, the length of a basketball court, and cover an area of 950 square feet. These are the largest solar arrays ever sent into deep space, and they need to be. Out near Jupiter, sunlight is only about 3% as strong as it is here on Earth. So the Clipper's giant panels are designed to collect every possible bit of solar energy to power the spacecraft's systems and instruments. These instruments, 9 in total, are some of the most advanced tools ever sent to the outer solar system. Among these are some of the most advanced cameras and sensors ever sent to the outer solar system, each designed to shed light on different aspects of this icy moon. Europa Clipper's visible light cameras will map the moon in incredible detail, covering far more ground and at far better resolution than any previous mission. These cameras don't just capture standard images, they extend slightly into the near-infrared and ultraviolet wavelengths, providing a richer view of Europa's surface. 2 infrared cameras will map the moon's composition, temperature, and surface roughness, giving scientists a clearer picture of its chemistry and how active it might be geologically. One of the star players in the imaging team is the Europa Imaging System, EIS. This system includes both a wide-angle and a narrow-angle camera, each featuring an 8-megapixel sensor. These cameras will produce high-resolution color images and even stereoscopic 3D views of Europa's surface. The EIS will help scientists study the moon's geology, measure the elevations of its icy ridges and valleys, and provide a critical context for data collected by other instruments. For example, it can pinpoint locations where the ice may be thin or where the ocean might interact with the surface. Perfect targets for follow-up studies. Another fascinating tool aboard Europa Clipper is the Europa Thermal Emission Imaging System, ETHEMIS for short. This instrument uses infrared light to detect heat, allowing it to identify warmer regions on Europa's surface. These hotspots could indicate areas where liquid water lies just beneath the surface, or where water has erupted onto the ice through cracks or plumes. By mapping these warm regions, ETHEMIS will help scientists understand where Europa's internal heat might be driving geological activity. The spacecraft is also equipped with instruments that use light to analyze Europa's composition. A spectrometer and a spectrograph will break incoming light into its individual wavelengths, much like a prism creating a rainbow. By studying how Europa reflects or absorbs specific wavelengths of light, these tools can determine what the surface and nearby particles are made of. For example, they might detect salts, organic compounds, or other materials essential for life. This incredible lineup of tools isn't just about looking at Europa, it's about understanding how it works. Together, the cameras and spectrometers will map the moon's surface, measure its temperature, and decode its chemistry, all while providing vital clues about the interaction between the icy shell and the ocean beneath. These insights could reveal whether Europa has the conditions needed to support life. Protecting all these sensitive systems is a top priority. Jupiter's radiation belts are among the most intense environments in the solar system, capable of destroying unprotected electronics in moments. To combat this, Europa Clipper's delicate components are housed in a specially designed radiation-proof vault. This vault acts like an armored bunker, shielding the spacecraft's brains from the worst of the radiation. While it carries out its mission, Europa Clipper's science tools are a technological feat, but they're also designed with precision and care for their unique roles. For instance, the spacecraft's radar will penetrate Europa's ice to help scientists figure out how thick it is and whether there are pockets of water trapped inside. This information could reveal areas where the ocean might be interacting with the surface, providing clues about how material from below could make its way to the top. The mass spectrometer will sniff out gases in Europa's thin atmosphere, analyzing them for chemicals like water vapor, carbon, or nitrogen, key ingredients for life as we know it. Meanwhile, high-resolution cameras will capture images of the moon's surface, mapping its ridges, cracks, and chaotic terrain in stunning detail. The spacecraft's journey will take it to Jupiter's orbit, where it will complete nearly 50 flybys of Europa. But this mission isn't just about Europa, it's about the bigger picture. Europa Clipper could change how we think about life in the universe. If its ocean contains the right chemicals and energy sources, it might be one of the best places to look for extraterrestrial life. Even if the mission doesn't find direct evidence of life, it will provide critical information that will guide future explorations. Someday, perhaps another mission will land on Europa, drill through its ice, and reach the ocean below. The power of deep space communication. The Europa Clipper spacecraft's communication system is vital for transmitting data from nearly 2 billion miles away, while withstanding Jupiter's harsh radiation environment. At the heart of this system is the radio frequency, RF, panel, located on the propulsion module at the Johns Hopkins Applied Physics Laboratory, APL, in Maryland. This panel controls the spacecraft's radio signals and contains electronics, switches, filters, and waveguides that route the RF signal between the spacecraft's 8 antennas. One major instrument using these antennas is the Reason system, which sends radio waves to Europa's icy surface. The waves bounce back, allowing the system to measure the distance to features beneath the ice and analyze material properties. Reason can identify areas where the ice is thinner, which may suggest interactions with the ocean below. The RF panel houses essential components like frontier radios, which generate signals, and power conditioners to ensure the system operates properly. Radiation monitors protect the equipment from Jupiter's intense radiation. Since this radiation can damage unprotected electronics, the RF system is housed in a radiation-proof mini-vault, keeping it safe while transmitting vital data back to Earth. Once tested at APL, the spacecraft is shipped to NASA's Jet Propulsion Laboratory in California for final assembly. The antennas undergo performance tests before the spacecraft is sent into space. The high-gain antenna will be crucial for transmitting data and receiving commands, though the process is more complex than simply sending signals. Europa Clipper must transmit data in small bursts due to the distance and limited solar power. It prioritizes the most critical data first, sending less urgent information later. With a 45-minute signal delay, Europa Clipper must operate autonomously, carrying out tasks without waiting for Earth's commands. Europa Clipper's communication system must handle a vast amount of data from its 9 scientific instruments, including cameras and spectrometers. These instruments will provide detailed insights into Europa's surface, ice shell, and potential ocean. However, only a fraction of the data can be transmitted at any given time, so scientists must prioritize key findings. The 45-minute delay in signal transmission means real-time operation is impossible. Europa Clipper's autonomy allows it to continue gathering and sending data even when communication is temporarily delayed. This is crucial as the spacecraft makes flybys of Europa, transmitting the data it collects, whether it's high-resolution images, temperature maps, or radar readings of the hidden ocean. Europa Clipper's communication system, alongside its advanced instruments, ensures the spacecraft can share its discoveries with scientists on Earth. This system allows the spacecraft to send signals despite the vast distances and extreme space conditions, helping scientists learn more about Europa and the potential for life on this icy moon. Each transmission brings us closer to answering the question, does life exist beyond our planet?